Good afternoon, everyone. Lovely hot day here. I should be outside enjoying myself in the sun, but nah, I'm too dedicated to my work. Here I am making a chemistry video for you instead. Actually, to be too honest, it's a bit too hot out there right now. Inside is the best place to be, and what could be better than doing chemistry anyway? Right, video continuing with topic 5.1 today. Going to look at three areas. One, the techniques used to investigate rates of reaction. Two, the methods used to investigate rates. You might be wondering what's the difference between those. There's a subtle difference which I'll explain. And thirdly, very briefly, the effect of temperature on the rate constant K. Right, let's begin by just looking at this slide. This is on the PowerPoint that I sent you. These are the five practical techniques used to monitor rates, or the five most commonly used techniques. You must be able to recall these and note that for each one you need to describe two things. One, what you measure. Two, the instrument you use to measure it. Note how that is the same for all of them. Drop in mass using a balance. Now, let's have a quick look at each of those in turn. Right, gas syringe is very straightforward. You have a reaction going on in a boiling tube that's connected to a gas syringe. You collect and measure the volume of gas produced. Sorry if it went out of focus for a second there. Now, another possibility is don't even bother connecting to a gas syringe, just carry out the reaction on a balance, and provided a gas is produced, it will gradually lose mass. Now, both of those techniques, either the gas syringe or the drop-in mass method, obviously only work for a reaction which has a gas as a product. And if you do have a gas as a product, you're rubbing your hands together, really thinking, oh great, it'll be easy to monitor this reaction. Should mention, by the way, there is a law of conservation of mass which states that in any chemical reaction the mass of the products will equal the mass of the reactants, and that is true. And if in this reaction you kept a bung on the boiling tube, the mass would not change actually. There's a bung on the conical flask, I should say. However, I should say the mass would not change until the point when the conical flask exploded. However, no, but because you let the gas escape, the mass will drop. So both of those techniques only work if a gas is produced. What if it is not produced? Well, some reactions involve a colour change. Sometimes you could start with a colourless solution and one of the products is coloured, so the colour intensity gradually increases. Could go the other way around, of course. You start with a coloured solution, one of the reactants is coloured, but the products are colourless, and the colour intensity gradually goes down. Now you can monitor the change in colour intensity. You need a special instrument to monitor that called a colorimeter. Colorimeter looks like this. You could put your red solution there in something called a cuvette, and you could measure the absorbance of light. The darker the solution, the more light is absorbed by it. So you could monitor the reaction by recording the absorbance at different points in time. However, even that technique, relies on a reaction in which there's a colour change. Not all reactions involve a colour change, and if it doesn't involve production of a gas and there's no colour change, then what are your other options? Well, one, some reactions involve a change in pH. The pH may increase or decrease as the reaction proceeds. You could use a digital pH meter to monitor that. Some reactions will involve a change in the electrical conductivity of the solution. If the reactants, are containing ions and the products do not contain any ions, or then there will be a decrease in conductivity over the course of the reaction. Vice versa, if the products are actually ionic compounds in solution, and therefore they will be mobile ions, but the reactants do not contain any mobile ions, then there will be an increase in conductivity over the course of the reaction. Right, let's put this in the context of an exam style question now. Of these 5 techniques, A, B, C, D and E, have this slide open on a computer or some sort of device would be good, or if you can't do that whilst watching the video at the same time, make a brief rough note of these 5 techniques A to E. Right, the type of thing you could get asked in an exam is you could be given a reaction, such as one of these 4, and asked to suggest what experimental technique could be used to monitor it. Now, there's often more than one possible answer. For each of these questions 1 to 4, I would like you to write the letters of the suitable techniques that could be used. There may well be more than one letter that's appropriate for each one. We just remind you of a couple of facts. Halogens as elements are coloured, as ions they are not. Also, there will, in fact, that's really all that I need to say. So, for each of these 4 questions, suggest which of these techniques would be appropriate for each one. Pause the video and have a go at it. Okay, quick run through those. Now, for number 1, does produce a gas. So you could go for A, the gas syringe, or B, drop-in mask. Those 2 are always interchangeable. If you can use A, you can also at the same time use B, because they both rely on a gas being produced. You could actually have also put D for that one, just because it would start off as an acidic pH, but the pH would gradually increase as the reaction proceeds, as the acid is used up. Now, number 2, no gas, so A and B are ruled out. However, iodine as an element is brown in colour, iodide ions are colourless, so colorimeter method C is the obvious answer for this one. There's no change in pH. There would be a slight change in conductivity, but just because there's actually 2 moles of ions on this side and 3 moles of ions on this side, but that's only a slight change, so it's probably not a good idea to use that, but you're not totally wrong if you suggested it. Now, number 3, again, no gas. The most obvious technique to use, bromine, is a sort of yellow-orange colour. All these ions are colourless, so there would be an increase in colour, so you could use colorimetry again. However, you could also use the pH method again. Again, the reactants are acidic, but the products are not, so you could measure the change in pH. You could also use conductivity for this one. This would be an ideal one for conductivity because there's a definite change. Loads of ions on this side, no ions on that side. So C, D and E are all correct, and ideally you've put all 3 of those. Number 4, no coloured substances at all in this, no gas either. Can't even use conductivity, 1 mole of ions on each side. Your only option is the pH meter, due to this reactant side being alkaline, products being neutral. So there would be a decrease in pH. Okay, that's it for techniques. Right, mentioned at the start of the video that, I was going to talk about practical techniques, which I've just covered, but also experimental methods. Now, experimental methods we've really looked at before. For experimental methods, you can either use continuous monitoring or initial rates. But you could be getting a bit confused here, thinking, wait a minute, you've given us 5 techniques, now you're giving us 2 methods. Well, what's the difference between these and what should I put for an answer? Well, if you ever get asked a question, what techniques could be used to investigate this reaction, you never answer continuous monitoring or initial rates. These are not practical techniques. The 5 practical techniques you've already been shown. These are simply two different, sort of wholly different methods which any of those techniques can be applied to. Now, just to give you an example, if you were using continuous monitoring, as we've mentioned before, it won't hurt to go through it again, you would do one experiment only, but you would take many different measurements at many different time intervals during that experiment. If, on the other hand, you use the initial rates method, you would have to do 4 different experiments, changing the conc of A each time, and measure only the initial rates. You'd only take a single measurement from each of these experiments, usually after only 10 or 20 seconds. Now, let's just put this in the context of the technique. Let's imagine you were investigating the reaction between calcium carbonate and hydrochloric acid we looked at before. Very quick reminder of the equation as shown there. Carbon dioxide is produced. And you could therefore choose to monitor the reaction using a gas syringe to measure the volume of gas produced. Now, you could do this using the continuous monitoring method, which would mean you'd measure the volume of gas at 10 seconds, 20 seconds, 30 seconds, probably all the way up to 240 seconds or 4 minutes. But that's just one experiment at which you take all those measurements from. The other option is to do 4 different experiments with a different conc of HCl each time, but in each of those 4 different experiments you would only measure the volume of gas after 10 seconds, a single measurement. So you get the initial rate, the rate right at the start of the reaction. So, to summarise, in any sort of investigation into rates, you have to decide on both. One, are you going to use the continuous monitoring or initial rates methods? But then secondly, you must decide which practical technique, which of these 5. So for any investigation, you must choose a method and a technique. So you might decide, well, I'm going to do the continuous monitoring method, only want to do 1 experiment, and the technique I will use is A, measure the volume of gas using a gas syringe, and I'll measure it every 10 seconds for 4 minutes. You could, on the other hand, think, no, I'm going to go for the initial rates method, and I'm also going to use the technique of B, measuring a drop in mass, and I'm going to change the conc of HCl each time, but I'm going to measure the change in mass after 10 seconds in each of the 4 experiments. So you would choose both a technique and a method in any investigation, but whenever you get asked an exam question, suggest a suitable technique that could be used. Let me emphasise, you must put one of these 5. You never put initial rates or continuous monitoring. Right, now there's 2 types of exam questions you could get on this actually. First type would simply be suggest a suitable technique that could be used to monitor this reaction. You'd be given an equation. That would be a 2-marker only, and you get the first mark for saying measure a drop in mass, second mark for saying using a balance. Occasionally though, you could get 6 markers on this. Now, a 6 marker might state something like, again, they'll give you an equation and then the question would say, explain how you could investigate this reaction using the continuous monitoring method. And this is an ideal template for your answer. You still include the technique in there, name a suitable instrument, and still state what you're going to measure. State that you will measure it at regular intervals. State what type of graph you then plot, and so on. Now, again, you've got this slide on the PowerPoint. I'll get you to actually copy this into your notes as mentioned in the email. One other thing there, this point about here about use a large excess of reactant A. What on earth is all that about? Well, you could carry out the experiment initially from your experiment, you don't actually get the conc of A, you actually just measure the volume of gas, but through calculation you can convert that in to a concentration of A. I won't dwell on how you do that for now, that will be covered in a practical, which we'll still hopefully get to do sometime this term. But let's just say for now you've converted them into concentrations of A at different time intervals. You could then plot that on a graph. Graph would look like that, and you'd say, right, done and dusted, it's first order reaction. Trouble is, it might not be, but let me explain why it might not be and how you can ensure that it actually is first order from the graph. Right, so just assume you're looking at the reaction between chemicals A and B, and in your reaction vessel you've added A at a concentration of 1m, B at a concentration of 1m at the start, and you find the concentration of A goes down like this over the time. Because every time 1 mole of A reacts, 1 mole of B also reacts, B's concentration should go down by exactly the same amount at each time interval. Right, you could plot a graph of A's concentration against time as shown before, classic first order shape, and you could say it's first order with respect to A. The thing is, it might not be, as I said earlier, but let's have a closer look at this and explain why. Right, it's worth considering why that graph is the shape it is. At the start of the reaction, the concentration of A is nice and high, would be 1m. If you do the tangent right at the start, you get the initial rate, and it's a high rate, nice steep line, nice steep gradient to that line. That's because the concentration of A is high. Now, halfway through the reaction, the rate is considerably lower, and that's to be expected. That's because the concentration of A has decreased. Because its concentration has gone down, the rate is going down. But wait a minute, is it a lower rate because the concentration of A is lower, or is it a lower rate because concentration of B is actually lower by that point? This might be at 20 seconds, say. Just notice one error on the B. That's better. Don't want Sarah complaining about my error. Now, the rate could have decreased because of the drop in concentration of A, but the rate could just as easily decrease because the concentration of B had dropped to 0.5 by this point. And it could well be that although A has dropped to 0.5 after 20 seconds, it could be the fact that A has dropped to 0.5 has had no effect on the rate. The rate is only slowing down because the concentration of B has also dropped. And it's actually the concentration of B that was a significant factor. Or it could be that it is due to the concentration of A dropping. We actually don't know from this data. How could we tell whether that drop in rate was due to the concentration of A or B dropping? Well, I'll show you how. Now, I'll have to set up the reaction like this to determine the order of reaction with respect to reactant A. Note how the initial concentration of A is vastly lower than the initial concentration of B. B is in a vast excess, in other words. Now, if here's the equation for the reaction, 1 mole of A reacts with 1 mole of B to make the products. If these are the concentrations of A over the first 30 seconds, what would be the concentration of B at each respective time? Pause the video, make a quick rough copy of this table and complete it, please. Right, here's some answers. After 10 seconds, half of A has been used up, so half of B has been used up. By 20 seconds, A has gone down to 30% of its original value. Sorry, realised another error there. Anyway, got it correct. B is down to 30% of its original value, and so on for 30. Now, if you've put that, you are a complete and utter idiot. It is not correct. Now, A and B react at a 1-to-1 ratio. That does not mean if half of A is used up, half of B is used up. It's not 1-to-1 in terms of proportions of their initial conc. It's 1-to-1 in terms of actual number of moles. And if 0.005 moles of A are used up in the first 10 seconds, 0.005 moles of B should be used up. So the true result should be, that is what the true result should be. Well done. If you put that all along, it's a 1-to-1 ratio numerically. The same number of moles of A are used as B. So they both drop by the same amount each time. Now what this does, however, mean is that after 10 seconds, A's concentration has dropped by 50%, B's has dropped by virtually nothing. It's an insignificant change in the concentration of B. Even after 30 seconds, A is down to 20% of its original concentration. B again has hardly changed. Still at 99.6% of its original conc, actually. B, whereas A is only at 20%. B is still more than 99% of its original conc. Now, if this time we get a pattern of the dropping conc of A that looks like this time we definitely can conclude the reaction is first order with respect to A, because during the experiment only A's concentration has significantly changed, B's has not significantly changed, and therefore if the rate of reaction is much lower when A's concentration has dropped, then it must be first order with respect to A. We couldn't argue at this point, oh, this could be just as easily because B is much lower than it originally was. It isn't. At this point in time, B is not much lower than it originally was. Only A is lower than it originally was. Slightly complicated, this point, I know. I've tried to explain it as fully as I can. It's probably something that's better done in class, I fully accept. But have a little think about what I've said. And in the end, it's only one small point. So say it's only one small point, and I will review this in class as well, but it does explain the first sentence on my slide there, although this time I've said use a large excess of A, and this would enable you to deduce the order with respect to B. In other words, the one that you want to deduce the order of must be the one that is not in excess. In my example earlier, I should have already got these to tie in with the slide, I used a large excess of B because I wanted to deduce the order with respect to A. Now, you could just as easily get a 6 marker that says, describe how the initial rates method could be used to investigate the order of this reaction with respect to reactant B. Again, you'd be given an equation. This time, your answer would have to be written out like this. This, if it was a 6 marker, make this point initially, you would actually put the names of substances in here. If this was iodine and sodium thiosulfate, you insert the names of the chemicals in. You would do 2 series of experiments. Of course, the first series you vary the concentration of B. The second series you would vary the concentration of A. That's if you have to deduce the order with respect to both of them. If the question only states work out the order with respect to reactant B, then leave out this line. But again, you've still got to put in the suitable instrument and technique. Just to try to fully clarify this is what I mean by the points on those slides. At first, keep A constant and vary the conc of B. You would do a first series of experiments like that. The next series, keep B constant and vary A. You would do a second series of experiments like this. This series would enable you to deduce the order with respect to reactant B. This series with respect to reactant A. And remember, this is the initial rates method we're talking about here, not the continuous monitoring. You just do a quick experiment, take a single measurement, time taken for 10 centimetre cube of gas to be produced, or the volume of gas after 10 seconds. You might just measure the absorbance after 10 seconds in each one, if it's a colorimeter experiment. Okay. Right, one final quick point, the effect of temperature on the value of the rate constant. You've got this table on the PowerPoint I sent you. Could you take a minute to complete the table by working out the value of K in each of those boxes, assuming it's first order with respect to both A and B, by the way. Hopefully you've worked those out. As I said before, first order with respect to A and B, so that would be the rate equation. To make K the subject, you just rearrange it to look like that. Now, inputting values from this first row of the table at 20 degrees C, rate is 1, A is 0.5, B is 1. Therefore, K will equal that, 1 over 1 times 0.5, and it's 2. And in fact it's 2 at all three of these experiments. Changing the concentration of A doesn't change the value of K, but of course it shouldn't. What does K stand for? Rate constant. It's meant to do what it says on the tin and remain constant. What about these ones at 30 degrees? Well, 30 degrees, A and B, by the way, are still at 0.5 and 1, but the rate is now 2. The rate was only 1 at 20 degrees. The rate has increased. Now, if the rate has increased, but A and B have both stayed the same, from our rate equation, you can already deduce, wait a minute, if this increases, and that stays the same, and that stays the same, the only way rate can increase, therefore, is if K increases. Just to confirm that mathematically, at 30 degrees C, the rate will be 2 over 1 times 0.5, and it comes to 4. So K has increased. And K will still be for the other two rows at 30. Again, confirming that K remains constant even if concentrations are changed. However, it doesn't remain constant when temperatures are changed. K was 2 at 20, it's become 4 at 30 for the same concentrations of A and B. So, in summary, the rate constant doesn't always do what its name suggests it should. It will remain constant unless the temperature changes. However, if the temperature does change, the rate constant will change, and if the temperature increases, the rate constant will increase. However, its value is not affected by changes in concentration of either reactants. Right, that's just about it. Finished all my explanations. It's now just a matter of doing the work, which I've mentioned on the email anyway. There's a few slides to copy into your notes. You've then got to do sections F and H of the question sheet. I'm leaving out section G for now on multi-step reactions because that's a little more complex, and I'll explain that in a separate video. But there's also a couple of other tasks I've set you. This is the 5.1 checklist I sent you a couple of weeks ago, and of course you've got all of these tasks as well as doing worksheets 1 to 3. We're only doing worksheet 1 at the moment. There's a number of extra tasks, and I've picked out a couple of these for you to do at this stage. The page 4 activity, the extended writing task on investigating rates. I've also set you one of the extension questions, which you can attempt if you wish to. You don't all have to do the extension question. I want you all to do the page 4 activity and the extended writing task. Those are compulsory. The extension question is optional, really for those aiming for an A or an A star. Okay, that's it for today. Hope you're all well. Hoping to see you soon, and bye for now.